I'm Chris Hudson, and I'm a researcher at the University of Bristol. I'm particularly interested in graphite, which is a huge decommissioning problem for the UK's nuclear industry. All except one of the existing nuclear reactors in the UK used graphite as a moderator, and the moderator's job is to slow down the neutrons to make the fission process, which generates that heat for the nuclear reaction, more efficient. All the fuel has been removed from the decommissioning reactors in the UK, and for those reactors that are yet to finish generating, the fuel will be taken out, and what will be left is these blocks of graphite material.
Hello, my name is Jared Menards. I'm a fourth year PhD student at the University of Bristol, and my project is on creating robotics for in situ graphite characterization. Graphite is a problem for the UK in particular. We actually have a considerable volume of graphite compared to the world. It's approximated at 86,000 tons, so it's a really big pressing issue. It's all been irradiated and we don't really have anywhere to put it. The proposed location is a geological disposal facility, but the problem with graphite is it's so bulky and it takes up so much space that there's a significant cost. It's around 43,000 per kilogram approximated. So it's a huge cost and investment, a huge volume investment for disposal of graphite.
The graphite itself is a little bit radioactive because it started out life in manufacture with some impurities, and some of these impurities have become activated. It's also radioactive with some beta emitters, such as carbon-14 and chlorine-36.
The problem with irradiated graphite is that it contains carbon-14. Now, compared to other sources of radiation and other radioactive waste, it's actually not that dangerous. You could block beta with a piece of paper, for example. The issue is the form it's in. Carbon-14 has high biological affinity, which means they can get into the biosphere, and over time and over generations, that would cause a significant increase in dose, which would cause an increase in stochastic effects. So whilst it's not as dangerous as, say, plutonium, you have to consider long-term effects.
The graphite that we used for our nuclear reactors in this country is now designated as intermediate level waste, or ILW. That means it's got to be treated in a special way, and at the moment it's contained within the reactor structures, so it's perfectly safe. Now, when the reactors are dismantled, we'll need to come up with a strategy of what to do with that graphite material. My ambition is to be able to recycle a lot of that graphite material in the next generation of reactors, and in order to do that, my research has been about looking at technologies and different processes we can employ so that we can correctly recycle the material, both the radioactive components and also maybe we can recover a lot of clean graphite. It's really important for us to understand exactly what's in the irradiated graphite, and we call that characterization. So we need to characterize the graphite first before we can feed it into a process where we can recycle it.
Robots are useful for characterizing graphite because it reduces the amount of contact that you need for humans. So humans wouldn't really need to be near the graphite, handle graphite, which means they get virtually no dose. The problem with sending humans into the area that the graphite is contained in isn't really with the graphite itself. It's that inside the reactor, there's a lot of metal that's been irradiated, and that contains gamma emitters, which are long-range and penetrating. So they're the actual main concern when trying to dispose of graphite with humans. So using robots, we can be more precise, we can repeat measurements consistently. So it's really about consistency, safety, and precision, which you get with robotics, and you can't really emulate that with humans.
The National Composite Centre have provided us with space to create a large mock-up of part of a nuclear reactor using some real graphite blocks.
This mock-up is made of graphite blocks that were never actually used, but they are of the exact same material as in the reactors. We've got a robot on top, and we've designed this probe system to go down the fuel channels. I contacted Clifton Photonics, who made the Raman probe, and I designed the robotics to be able to deploy this in situ.
Part of our work has been to make a probe that will contain all of the sensors that we think we will need to understand what the constituents of the graphite are in the irradiated state.
You'll see it inspect with a laser, We have infrared camera footage from inside the fuel channel. We have Raman spectroscopy being deployed in situ, remotely, using robot systems to drive over the pile cap, deploy the probe down, and actually get readings without having to into the lab. If you have a problem with bringing the materials to the lab, you bring the lab to materials, and that's what this robot does. Raman spectroscopy is a light-based technique that chemically analyzes the surface. So you shine a laser at the material and then you measure the reflections, and based on how much energy the light has lost, you can tell properties of the material bonds and the structure of the material. And this can be up to 50 meters away from your actual workstation where you're processing the data. What this means is you don't actually have to take the samples out to be able to chemically analyze them. You can just send the standoff system down and analyze it in situ.
We're doing all this graphite research in order to reduce the overall long-term cost to the taxpayer. We're working with several different organisations. For example, we're working directly with Manchester, having demonstrated that our robotic technique, including the probe, is capable of making measurements within graphite fuel channels. We're planning in the near future to try out this technique on a real nuclear reactor that's undergoing decommissioning.
There's a lot of work that can be done to further develop this concept, but this is a first demonstration of taking a traditionally lab-based technique into a radioactive environment.
In its totality, our research programme into graphite is going to be really, really important for the UK because it should allow us to avoid disposing of the graphite material that we used for reactors in the past through being able to divert nuclear waste from long-term storage into reuse and new applications, including the new nuclear fleet for the UK.